Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Fatia Azira binti Muhammad Shukri and my number matrix 1250779. So I'm going to present for task 1 and the given data is from group 14, which is the initial concentration C naught is equal to 185 milligram per liter. The concentration after 5 hours and the CT1 is equal 111 milligram per liter and the target concentration is 35 milligram per liter. So our objective is to determine the concentration function and estimate the time required to reach the target concentration. So the pollutant concentration follows the exponential decay model. So we get C of T equal to C naught e to the power negative KT. To determine the decay constant K, we use the known data at T equal to 5 hours. So substitute the given data, so we can get the K is equal to 1 over 5 multiplied by the ln 185 divided by 111. So after calculation, the value of K is approximately 0.106. So therefore, the concentration function become the C naught equal to 185 to the power negative 0.060. So this question now can be used to predict the pollutant concentration at any time. So next, we determine the time required for the pollutant concentration to reach the target concentration of 35 milligram per liter. So we start with the concentration function that we obtained earlier, which is C of T equal to the 185 e to the power negative 0.1060. So since we want to find the time when the concentration reaches the target value, so we substitute C of T with the 35 milligram per liter. So after that, we can rearrange the equation so that the exponential term is on one side. Then we apply the natural logarithm to remove the exponential function. And then after calculating, we finally get the T is equal to 15.70 hours. So now let's move to the result and discussion. So based on the developed exponential decay model, the pollutant concentration at different time interval was calculated as shown in the table. So from the table, we can see that the pollutant concentration decreased continuously over time. So initially, the concentration is 185 milligram per liter at 0 hours. And after 5 hours, it decreased to 111 milligram per liter. So the concentration continues to decrease to 66.6 milligram per liter, 39.9 milligram per liter. And then after the model predict that the target concentration of 35 milligram per liter is achieved after approximately 15.70 hours. So after 20 hours, the concentration further decreased to 23.9 milligram per liter. So now let's take a look for the graph. So based on the graph, we can clearly observe that exponential decay trend. So the pollutant concentration decreased rapidly during the early hours, and then the rate of a decrease becomes slower as time increase. So this happens because the pollutant removal rate depends on the amount of a pollutant remaining in this reservoir. So as the concentration becomes lower, the rate of decrease also becomes slower. So overall, both of the table and graph show that the exponential decay model accurately represent the behavior of the pollutant concentration over time. So in conclusion, the exponential decay model C of T equal to 185 e to the power negative 0.1060 successfully described the decrease in the pollutant concentration over time. The calculated decay constant is a K equal to 0.106, and based on this model, the pollutant concentration reaches the target value of 35 milligram per liter after approximately 15.70 hours. So therefore, this mathematical model is useful for predicting pollutant concentration levels and supporting effective water quality management. That's all from me. Thank you.
Assalamualaikum, and my name is Batrisha Balkis binti Muhammad Pairuz. My number matrix is 1250221. For task 2, we analyze the response of a data acquisition module used in the IoT-based water quality monitoring system. The system is represented by a second order differential equation, where L is the inductance, R is the resistance, C is the capacitance, and QT represents the electric charge over time. For group 14, the given parameters are L equal to 0.28 Henry, R equal to 560 ohm, C equal to 220 microfarad. The objective of this task is to determine the complete solution of QT, calculate the value at 0.01 second, sketch the response profile, and discuss the system behavior. First, we substitute all the given parameter values into the differential equation. This gives us 0.28 Q plus this gives us this equation. Next, we evaluate the response at t equals 0.01 second. So by substituting the value into the complete solution, we obtain that Q 0.01 approximately to 1.17 times 10 to the power of negative 9 coulomb. So this value is very close to the zero. So it shows that the electric charge decreased very quickly within a short period of time. This graph shows that the response of the system at the beginning, the charge starts at 2 times 10 to the power of negative 6 coulomb. As time increases, the charge decreases exponentially until it approaches zero. There is no oscillation or repeated up and down movement. The graph clearly shows that the response is smooth and stable. So based on our results, we conclude that the system is an overdamped system, and this is because both characteristic roots are real and negative. As a result, the response decreases smoothly without oscillation. The charge eventually approaches zero, indicating that the system reached a stable condition. Therefore, the data acquisition module produces a stable response which is suitable for reliable water quality monitoring application. In conclusion, we successfully obtained that the complete analytical solution for QT evaluated the response at 0.01 second, analyzed the response graph and showed that the system is stable because it has an overdamped response. Thank you very much.
Before we move on to the last task, which is task 3, let me introduce myself first. My name is Muhammad Akmal Hakim bin Abdul Rahman and my metric number is 125039. This task focuses on analyzing a periodic sampling signal using the Fourier series. For our group, the given function is ft equal to 17 minus 0.5t, where the signal is defined from 0 to 17 seconds and repeats periodically. The objectives of the task are to determine the Fourier series representation, approximate the signal using the first three non-zero terms, estimate the signal value at 17 at t equal to 17 over 2, and compare to the estimate value with the exact value. This analysis demonstrates how Fourier series can represent periodic signals commonly used in engineering applications. For question A, we substitute L equal to 17 into the Fourier coefficient formula. After evaluating the integrals, we obtain A0 equal to 25.5, AN equal to 0, and BN equal to 8.5 over N pi. Since all cosine coefficients are 0, the Fourier series consists of only the constant term and sine term. The final Fourier series representation is shown at the bottom of the slide. While for question B, we approximate the signal using the first three non-zero Fourier terms by substituting n equal to 1, 2, and 3. This produces the simplified approximation shown on the slide. Next, for question C, we evaluated the approximation at t equal to 17 over 2, which is 8.5 seconds. Since the sine terms become 0 at this point, the estimated value is 12.75. To solve this problem, we use the Fourier series formula for a periodic function defined over one period where its condition from 0 to the limit. The coefficient A0, AN, and BN were calculated using the integral formula shown on this slide. This coefficient determine the contribution of the constant, cosine, and sine components to the overall signal. Lastly, for question D, we compare the estimated value with the exact value obtained from the original function. Both values are equal to 12.75, resulting in an absolute error of 0 and a percentage error of 0%. This shows that the Fourier series approximation is exact at t equal to 17 over 2. In general, adding more Fourier terms will improve the approximation over the entire signal period.